So, ladies and gentlemen, by the local time it's 4 o'clock. I know that it's 4 o'clock 1 minute on the clocks, but let me make it easier for the speaker to use the local time. So let me welcome our speaker, Professor Yurii Nesterov, here in the big lecture room of the DAG. To make a long story short, let me tell you that this is his official visit to the University of Debrecen, and maybe the background of this visit was that due to his cooperation with some researchers with Tibor Illich at the Corvinus University, he decided to give a series of lectures at the Corvinus University, and in order to be hired by the university, he had to get a Hungarian PhD. So, how to get a Hungarian PhD? Our university is open for such possibilities, and his contribution, his mathematical contribution, is certainly several thousand times bigger than what is required for our PhD degree. So he finally got it, but he missed the official and festive event where he could get the diploma in hand. So I asked him to come to Debrecen at least once. So maybe this is the beginning of something. So that should always be a first day. So I asked him to come to Debrecen and to thank his degree by giving a talk here at our university. But to give you a little some details about him, I'm not going to read everything which can be found on the internet, but there are some very interesting details. So he graduated in Russia in 1980 at the Moscow State University, and his main field of research is optimization theory, and I would say that this field, optimization theory, is one of the central fields which was that time really blossoming at Russian university, particularly at the Moscow State. I also learned a lot from the book of Kirsanov, Tikhomирov, and Yoffe that time. In fact, I had to give my first course on theory of optimization, so I was able to use the textbooks of Russian writers. So he graduated in 80 and got his PhD in 83. And a very interesting thing is that he published a paper which was part of the PhD in the Dokladnie Akademickich Nauk. And this paper alone, which was written in Russian, and it was written during the so-called Cold War. Some people know what was the Cold War. So there was no big communication, so to say, between the East and the West. And so this paper got about 7,000 citations, which was published in 83. I think that's your one author, this is your most important, most famous one author paper. He had several lecture books also, which has tons of citations. Altogether, if you visit the Google Scholar page, then you will see that the total number of his citations is about 50,000. So, which I would say is it's not only amazing, it's really very, very, very important. So he was decorated with several awards. And let me mention that first he received the so-called Danzig Prize, which is the most important prize in optimization theory. And he got this in 2000. Then he got the John von Neumann Theory Prize in 2009. The Euro Gold Medal in 2016, and the WLA Prize in Computer Science for Mathematics in 2023, which is, I think, it's a Chinese award. And the importance of this award could be compared to the Kyoto Prize or to the Wolf Prize. Maybe this is more known for you. His field of research are convex optimization, semi-definite programming, nonlinear programming, numerical analysis, and applied mathematics. Let me mention that there are two kinds of people, I mean, this is a simplification. But some people are happy about existence and uniqueness of solution, and some people try to construct methods how to find a solution, if there is a solution. And I think he belongs to the second group, and he developed several important algorithms and fast algorithms to solve convex optimization problems. And I think today's talk is somewhat related to that field. So with this introduction, let me invite Professor Nesterov to deliver his lecture. Thank you for attending our invitation.
Okay, thank you very much for this nice introduction. So it is my pleasure to be here and to discuss finally some interesting mathematical questions with local people. You know, my main field is optimization, numerical optimization. So I am interested in constructing of numerical methods. So on the other hand, so I understand that the most people here are mathematicians. So they are mostly interested in mathematical theories, some mathematical questions. And therefore today I decided to show you some methods for very challenging kind of optimization problems, maybe the most challenging, the most difficult problem in the convex analysis. So this is a problem. This is a problem related to variation inequality. So, and first I would like to explain you why this class of problems is important and why it is especially difficult. So, variation inequalities is defined by a continuous operator V, okay, which maps finite dimensional vector space to the dual space. The dual space is the space of all linear functions on our primal space. So we're using this terminology despite to the fact that we always work with finite dimensional spaces. Therefore, in some sense, everything can be identified with Rn, so the primal and the dual spaces. But from a viewpoint of interpretation, it is very important to keep these spaces different. So the spaces of our diffusion variables and the spaces of linear functions on our decision variables. Okay, so this is the primal view of F. Now, what is the variation inequality problem? So we need to find point X star which belongs to our feasible set Q. So feasible set Q is always assumed to be convex, which means that with two feasible variants, with two possible variants of compromise solutions between these two variables are also feasible. Okay, so at this point should satisfy this variational principle. So if we take the value of our operator computed at this point and look at all feasible directions from our point X star to any point in our set, then the angle between these two directions is positive definite. So this principle actually has many interesting applications in economics, game theory, and mechanics, and so on. So this is indeed one of the most general and interesting, let me say, variation principles so in convex analysis. So this is the definition of our problem, so X star. So it can be written somehow in the equivalent form, where we change X star there by arbitrary point. Now we say that from every point X, so the direction from X to X star is attractive. So if we are staying at the point X, we always want to go towards this direction X star. And this will be again the solution, called the solution of our variation inequalities. Actually, if our operator is good, V of X is continuous, then these two definitions of the solutions are equivalent, so it can be easy to prove. But in order to be able to solve this problem, yes, in order to approximate this solution, we need one more condition on our operator, okay, which is called monotonicity. What is it? So we compute the Jacobian of our operator, v prime of x. This is the matrix, or linear operator from prime to the dual space. And this operator, which is not necessarily self-adjoint, but it should be positive semi-infinite. So it should satisfy this condition. So under these assumptions, well, we already can prove many things about the good things existence, sometimes uniqueness of our solution, and this is more or less the standard assumptions. Now, what this is, as I told you, actually the most general formulation in convex analysis, and of course it is interesting to see what are particular cases which are inside this problem class. Okay. First of all, the simplest variance of this problem is when our feasible set, so this guy, is the whole space. Then, so this just variational principle is reduced to the solution of system of nonlinear equations. Yeah? The dimension of the primal space is the same as the dimension of the dual space, therefore it is the equation which maps n-dimensional space to n-dimensional space, so we have system of n equations with n unknown, if you will. Just solve the equation which has this additional condition of monotonicity. Now, minimization problems, another important class of problems in convex analysis, we just minimize function, differential function on our set K. So then, so it can be posed as variational inequality problem. So when we take the value, the operator is the gradient, which is the operator is the gradient of our function at point x. Yes, so gradient is element of the dual space. So therefore, this is an operator from the primal space to the dual space. So it fits exactly our framework. And then, so this condition, so condition variation principle is what is called an optimization. So the first order optimality condition. So characterize the point of the solution of our problem. Now, there is a big class of the games, for example, zero-sum matrix games, which are defined on the primal and dual strategies, so which in each strategy is usually in the simplex, so mixed strategies. And then, so again, so this can be posed as the variation inequality problem if we choose our operator v of z. Z is the set of primal and dual variables, which belongs to this simplex. So, which is just linear operator, so with our multiplied by z. And what is interesting here is what is this operator? This operator, so for zero-sum matrix gate, is a skew-symmetric matrix. Yes, so here matrix A transpose it here is minus A. Therefore, if you multiply it 2 times by the vector u, so u is the competence xy, so we get 0. So this is so-called skew-symmetric matrix. But of course, so this condition is satisfied. So, but instead of inequality, we have here always the equality. So this is one more examples, and again, so important in economics, important class of zero-sum matrix. Now, how we could solve these variation inequalities, and what would be the possible optimizations? Now, in all problems actually of optimization, the first method which we should try for solving is the simplest so-called gradient method. Let me just recall you what is it. So the gradient method is usually defined in the simplest way for unconstrained minimization problems. We have a function, differentiable function, no constraints. And then the classical gradient method proposed by Cauchy 150 years ago is like that. We are staying at the point xk. We compute the direction of the gradient. From the analysis, we know that the direction of the gradient is a direction of the fastest increase of the function, but we want to minimize our function, therefore we go in the opposite direction with some step size, positive step size h, we move along the opposite directions, and we hope that so it will be the better, the next point will be the better than the previous one. How we prove the convergence of these methods? Okay, assume that our function f has Lipschitz continuous gradients, which means, okay, so the Lipschitz continuous gradient, the difference of the gradients, norm of the difference of the gradients in 2 points, so is smaller than distance between these 2 points multiplied by the Lipschitz constant. Then we can look what happens with the distance to the optimum. Yeah? So from this move, so we assume that the norm here is Euclidean, we can write down, so what is the new distance to the optimum? So open the brackets presenting xk plus 1 in this way, we can easily see that the new distance is equal to the expression on the right-hand side. Now let us look at this term. So this is the old distance. So this, since our function is assumed to be convex, so this scalar product can be bounded from below by the difference of the function value in xk minus fx star, so it is positive. And this square norm of the gradient, because of the Lipschitz continuity of the gradient, also can be bounded by the difference in the function. In any case, so this is, it should be less or equal, so this is distance is less or equal than that one. And here you see what happens actually. So what are our abilities? So we minimize our function. F star is the global minimum of our function. Therefore, this quantity is positive. Therefore, if we take h small enough, then so this quantity will be positive. So which means that every step in our scheme decreases the distance to the optimal point. This is the main property actually, which is used in all, or let me say, almost all optimization schemes. So if we choose h small enough, here we can even say what is the best h, so we can decrease the distance to the optimum. So thing which is really very important for proving the convergence of the schemes. Now, what happens with variational inequalities? Let us look. Let us v of x is just cx, and we put cx here. Then this scalar product, if, for example, x star is equal to 0, then it will be just equal to 0. Which means that after a single step, so we increase the distance to the optimum. Yeah? This is a very bad sign. So the simplest strategy, which is usually related to the gradient type method, so gives us completely contradictory results. Instead of coming closer to the optimal point, we increase the distance, to the optimum. And we cannot do anything with that, because so even if we play with the size of step size, so since this guy is 0, so distance is always increased. Okay, which means that for this simple problem, so if we apply the gradient method to find the root of variational inequality, the gradient method simply diverges. Because we can say, so this is the reason is that, so here we have unbounded feasible set, we have no constant. Okay, let us look, can we have some help with the constraints? So this is again the variant of the gradient method, but now we have constraints. So we move along the direction of anti-gradient, yes, with some step size, and after that the result is projected on our feasible set. So let us look what we can do with that. Situation is a little bit better. Yes. So let us look what happens with the distance to arbitrary point x. So it can be, after this step, it can be developed like this. And from the optimality condition for the projection for this minimization problem, so we can estimate this guy from above using this scalar product. Okay, this is our main relation. The distance to some any point x from the previous point is compared to the distance from the next point is compared with the distance to the previous point. Okay, let us look what do we have in the right-hand side. Yeah, so here it will be convenient to replace this v of xk by v of xk plus 1. Okay, and we estimate the difference of these two guys using this by this term. So this is our main inequality. Now we see what happens. So we want to control somehow the distance to the optimum. Therefore, for us, it will be important to maximize this in ORK to see what is the maximum value. Yes, ORK, so this maximum can be found easily. And from the monotonicity, so we can replace this scalar product by this scalar. If you see, so that from monotonicity of our operator V, so this is always greater than. Now we have very convenient construction where our point of our process enters linearly. Therefore, at this moment, so we are able to sum up all this inequality and write down something for the average point. You see, so the right-hand side of this inequality is linear in xt. Therefore, if we compute the average, the sum of these inequalities, so in xk plus 1, it will be just the averaging of all the trajectories. So if we do that, so just sum up all these guys, and denoting by x bar k the average points of x of our trajectory, then we get the following inequality. So which is actually for variational inequality is more or less the maximum what we can do in this framework. So from this summation of these two guys, we get the maximum of this measure. You see, maximum of this stuff in S. So it depends on the point, our average point, x bar of k, is can be bound. So what we have finally in the right-hand side. So our set is bounded. So we bound, so this is squared norm by d. So finally in the right-hand side we something like that. So this is already something, maybe not very good, but at least something which we can say about the efficiency of this process. What do we have in the left-hand side? Yes, so from the definition of the optimal point, optimal solution of variational inequality, so we see that this proximity measure, as it is called, is always non-negative. Yes, so this is the maximum in all points. Therefore, if we take x equal to x bar k, this is at least 0, which means that maximum is always non-negative. On the other hand, at the solution point, so if x bar would be the point x star, so on definition of our variational principle, it is 0. Therefore, this is the correct proximity measure. This is the correct proximity measure of our average point xt. And we see that in the right-hand side, we have something which we can decrease with the correct step size strategy of choosing hi. For example, if we choose hk proportional to 1 over square root of k, okay, then it can be proved that the right-hand side decreases proportional to 1 over square root of k. So which means from the viewpoint of optimization theory, for our proximity measure, we get the rate of convergence proportional to 1 over square root of k. In optimization, the rate of convergence so plays very important role as a characteristic of our processes, so we can guarantee some have worst case, this is the worst case guarantees for the behavior of our scheme. 1 over square root of k is not very fast rate, so you can play with the numbers. For example, after 100 iteration, you have here only 1 over 10, which is not too much, but still, so there is at least something. But again, from the theory of context optimization, we know that it is not optimal. It is not optimal because in theory optimization we have lower complexity bounds, which say that there is no scheme for solving variational inequalities which converge faster than 1 over k. Yes, so which is much better than 1 over square root of k. Here we get something which is not optimal. On the other hand, and on the other hand, from the viewpoint interpretation, so our method is indeed very strange. Fortunately, I have no blackboard to draw what is the behavior, but no, the fact that after one step, so the distance to the optimum can only increase. Okay, this fact is still valid for our scheme. We cannot change that. Therefore, look what happens. We have bounded set, and we generate the distance of points with the increasing distance, sequence of points with the increasing distance to the optimum. So just imagine that we have some, I don't know, set, which means that in the limit, our trajectory will go along the boundary of this set. So there will be a kind of orbit. It will never go to our solution, which may be somewhere inside of the set. And the fact that we still have the convergence is due to the average. So even our sequence goes along the boundary of the set, the average point can converge to the right solution. But it is clear that from the practical point of view, this trajectory is very, very bad. So it cannot provide us with the good adjustment process or whatever, which is important in applications. Okay, this is the reason why actually many years ago, in 1976, so-called gradient, extra gradient method, so made, let me say, sensation in this field when people managed to found very simple scheme which has the optimal rate of convergence. The scheme looks very strange. So we are staying at the point xk. We do one extra gradient step with some step size, project at our point. At that point, we compute the value of our operator. And after the move using this operator from our own point, the point from which we had this one extra gradient step. And this will be our point. Yeah. So this strategy during many years it didn't have any reasonable interpretation. So people, so and the rate of convergence of this scheme is already much better than just the rate of convergence of the usual gradient method, was proportional to 1 over k, but really during many years, so we didn't understand what happens here. Yeah, so actually there was only explanation, say, heuristic explanation, which tells us that actually if we move in the direction of anti-gradient, then this direction as compared to the point xk will be better somehow placed with respect to the direction to the optimum. But all of that indeed didn't have any convincing proofs. Therefore, so up to now it was really a miracle. While we had this effect for the extra gradient method, and today, so I just want to present you some, let me say, explanation. So what actually happens with these extra gradient gradients. So this question actually, so which is also interesting today, just because now, so with the recent development in optimization theory, we have many new methods which also suffer from the impossibility of decreasing the distance to the optimum. Yeah, so the big family of new optimization schemes which is related to the high order methods, again, so automatically they do not have reduction of the distance to the optimum. So this simple property which we have for free for the gradient methods. And indeed, so it becomes interesting to find some, let me say, general technique which help us to bounds somehow the optimization method, and which works in different situations, in particular here in variation inequalities or in higher order methods. So just to see how we can do that, just because also in many applications now, so we need from our optimization schemes somehow so-called hot start possibilities. Hot starts mean that if our starting method is close to the solution of our problem, then the complexity of our problem becomes smaller. So therefore, the quality of initial point indeed matters. So this is so-called the hot start ability. Up to now, so for variation inequality, we didn't have this time. Okay, so in order to explain your main idea of this scheme, so let me just describe the class of the problems, which is a little bit wider than the class which we considered before. This is so-called composite variational inequality. Again, in this composite variational inequality, we have our main object is continuous operator from the primal to the dual space, but also we have a closed convex function psi. Okay, this is our composite term in the variation inequality, which in our optimization problems we mix somehow with this operator. So this is the definition of the solution of composite variation inequality. So as before, we have this part of the problem which depends on our operator. So in principle, without psi, there should be, this guy should be greater or equal to 0. But now we add here this function psi, which is a simple function. Okay, and with this simple function, so we have these additional terms in the left-hand side and right-hand side of our inequality. Okay, so why this is interesting to consider this composite variation inequality. So is that actually the main condition for solvability of this problem remain the same, the monotonicity. On the other hand, so with this composite term, so we can indeed put in this framework many interesting formulation of variational inequalities. Okay, for all of that, we will use again the modified our merit function. You remember before we had only this guy, so the guy which depends at our point x bar linearly, so supremum of x. Now we subtract here some terms which depends on the function psi. Okay, so in the important cases, so first we cover in this case the constraint variational inequalities. Okay, so then function psi should be just the indicator function of some simple set Q. So for application and optimization, actually, so very often, so people use here instead of function psi, so the something simple like L1 norm, sum of absolute values of xi. And it can be proved that in this way, so with this simple function psi, so we will be able to find the solution with a small number of non-zero elements. So the modern formulation in machine learning, like lasso problems and so on, they work exactly with this type of function psi. So there are indeed many applications in optimization. Therefore, and for variational inequalities, this is also true. If we want to find the solution, approximate solution for variation inequality, the small number of non-zero elements, so we should put here instead of psi, the sum of absolute value of the coordinates x. So the main condition for this function psi is, of course, that it should be simple. Simple means that with this function psi, we should be able to solve some auxiliary optimization problems. We will see in a moment what are auxiliary optimization problems which we need in our framework. Now, let us pick a so-called reduced gradient cut for convex for composite variation. So assume we have some point V bar in our domain of our problem. Again, so in our problem now we have domain of psi, which can be considered as kind of feasible set. So inside of this domain, so operator and function psi are well defined. So assume we have some feasible point. Now, so at this point, we want to find first a cutting plane which separates our point V bar from the solution of our problem. Okay, this idea actually in optimization is very powerful, and very often it is used in different methods of finite dimension, like ellipsoid method or center of gravity method, and so on. But here we will try to use this idea for variational inequalities. What does it mean? Cutting plane which separates V bar from the solution. So it is an inequality, linear inequality, which for us it will be convenient to write down in the following way. Yes, so there is some point x plus such that our function, cutting line function at the point V bar is bigger than the level of x plus. Okay, this thing is greater than 0. And on the other hand, the level of this function at the solution is smaller than x plus. Okay, so we have this, let me say, cutting plane condition. Cutting plane condition, again, so this is a standard thing in the optimization theory. So, but for us it is important first that, so this cutting plane strictly separates V bar from the solution x star. You see here, this is the strong equality. Of course, and of course, so in order to have this cut efficient, we need deep cuts, which means that the difference between the left-hand side and the right-hand side is big enough, and we can measure this depth. Of course, in optimization, so as I told you, so we often use this separation principle, but in separation, the optimization, the situation is much simpler. In optimization, we always take x plus equal to x bar. What happens then? So here we will have 0, V bar is equal to x plus. And then in the right-hand side, so we'll have something negative. And in optimization, so it appears that it is possible to prove that this difference between 0 and this value of the cutting plane is bigger. So there are several measurements, convenient measurements for deepness of this cutting optimization. For example, it may be difference in the function value, or squared distance to the optimum, or squared norm of the gradient. So all these things for different problem classes we can put between this 0 and this value of the cutting. Yeah. For variational inequality, this is just impossible, as we have seen, because this value can be equal to 0. Yes, remember the skew-symmetric matrix. We cannot play with the deepness of this right-hand side. Therefore, so the only possibility for us is to try to ensure the depth of the cut using the left-hand side of this inequality. Okay. Only by the left-hand side of this inequality, and so in order to use this deepness in our, let me say, reasoning, so we introduce the new concept, so-called the universal step size. What is it? This is the depth of this cut, so it must be strictly greater than 0, normalized by the squared norm of this cutting. So we'll see how this universal step size it works. Okay, and but our goal again, so this is the main, more or less, what defines our optimization scheme. Again, we're staying at V bar, and we need to find the point x plus such that the depth of this cut is sufficiently positive. Okay, so if again, sorry, I have no blackboard. So if you look at the one-dimensional picture, what happens? So for just imagine, so we have the shape of our function like that. We're staying here, and we move towards the direction of the minimization of our function. Then, so the condition means that we shouldn't go up to the zero scalar product of this guy with that. So which corresponds more or less for one-dimensional minimum along this direction. So we can stay before. So we stay on the negative slope before we reach the zero value of this scalar. But again, so this is optimization derivation. So what is the structure of our method? So we update the sequence of Prox centers. For each Prox center, we compute the point where with the cutting plane, so which satisfies our deep cut condition. So I will often refer to this as a deep cut condition with this universal step size. And after that, we work somehow with the set which contains the optimal solution of our problem. But note that this set, so the domain, so intersected with this cutting plane, so which contains X star, is strictly separated from our current approximate DIT. This means that we can be sure that the distance to these points from this set is under our control. Now, so in this framework, of course, it is important how we compute this cutting plane, VC at this new point xt plus 1. And for that, so we can apply very simple observation, which tells us that suppose we have an auxiliary monotone operator on our domain, yes, with which we solve auxiliary optimization problems. Okay, this is a simple auxiliary operator, and we solve for that auxiliary optimization problem of that type. Yeah, so you see, this is definition of the solution of variation inequality for this simple auxiliary operator AOT. Exactly what this is our problem. Then it appears that this value of operator at the new point, it is the theorem, can be used in order to cut our solution from the optimal point. So we can define then reduce gradient at the point T just by subtracting this value from our operator theory T, and then we get this our famous V psi of xt plus 1, which is doing a half of the job. It cuts the optimal solution from our point xt, from our point x. Yes, remember the definition of the cut. So the half of the job can be done using this auxiliary minimization problem. What remains now is to choose an appropriate auxiliary operator A such that the left-hand side of this inequality is deep enough. Okay, so this can be done in different ways, but all these ways, they can be after that included in so-called primal reduced gradient. Again, so I show you the general form. So in order to describe it, we need so-called Prox operator. Look what it is doing. We're staying at the point D. So we have a linear function which defined of J, we multiply it by H, and we minimize this linear function with this augmented term on our domain. Yeah, so this standard definition of the Prox operator. Now, what then, how we use it in our scheme? we are staying in the prox center VT. Somehow we compute our cutting plane defined by through the point xt plus 1, and this guy now is used for generating the new prox center in our sequence. Just we put this guy here instead of v, we put v of t. We solve this problem, and this is it. So this is our minimization. So you see, the scheme is again up to this moment it's very general because we didn't say anything about the way of generating this cutting plane, but still, so about this scheme we already can prove something. We can prove something, so which gives us this inequality, and this inequality tells us that if our cutting planes are good in terms of, remember this universal step size, so which actually is related to this term and related to this term, then actually we have a kind of convergence for all our objects. Okay, this is again absolutely general theorem, which is valid for arbitrary way of generating the psi, but if we will be able to relate somehow this guy with the proximity measures of our problem, then we will have the convergence rate for this stuff. Okay, the output of this algorithm is again the average point of our points where we compute this cutting. And of course, so from this it is clear that our goal is try to generate this AI so as big as possible. They relate to the convergence. Okay, this is the general scheme. Let us look how it works for variation. So I will show you the methods for high-order method for composite variation inequalities, just because so the explanations and the theorem on the convergence of this process so is working for any order of the schemes. So let us look what does it mean for variation inequalities. So for that we need to describe the Taylor approximation of our operator view. What is it? So in the right-hand side, you see just the usual Taylor expansion, which starts from I equal to 0. I equal to 0 corresponds to the value of our operator. After that, I equal to 1, this is the Jacobian. So after that, this is the second derivative, directional derivatives. All these things are directional derivatives for certain order of our operator at the point x, which means that the dimension of all these objects is the same. It is the dimension of the dual space. So all of them, if you want, are the vectors, linear functions. Okay, so if we know the formulas for the operator D, then we can apply differentiation rules and compute this again. Now, but of course, so in order to use this guy, so we need to solve some optimization problems or variation inequalities problems which are related to this Taylor sequence. So directly we cannot use that, but if we assume that the last derivative is Lipschitz continuous, then it appears that we are able to form the augmented Taylor approximation. What is it? To the value of the Taylor series, we add the gradient of corresponding power functions. Power functions corresponds to the last derivative with Lipschitz property. And it appears that this operator, again, so the dimension of this guy is n, so it lives in the dual space. So then this augmented approximation is monotone, is a monotone operator, which means that we are allowed to use this guy in our auxiliary problems if we choose this constant big enough, namely bigger than Lipschitz constant for the high derivative. So if we do that, okay, then we are able to compute the tail tensor step for our variation inequalities. And then, so we can use this guy in our primal scheme. So how do we use it? So we just use it as an auxiliary operator for defining the cutting plane. You remember the reduced gradient rule. And then it appears that, so we have this property. So this is for free. We already have seen this, the simple inequalities, cutting plane inequalities. But also we are able to prove that our universal step is big enough. It is big as compared with the size of this deep side of T, which is there. So all of that is more or less the simple exercise in nonlinear analysis. So this is almost the end of the story. So using this description of the quality of our universal step, we just plug in the corresponding object and the theorem which we have in the previous slide, and now we can prove the rate of convergence for our merit function. Yes, so we look what happens at the right-hand side. Yes, so for us it is important to see the dependence decrease of the right-hand side as a function of the number of steps. For that, here we have 1 over t to the power p plus 2 divided by 2. What is p? P is the order of the derivative, yes? Lipschitz continuous derivative. So for classical situation, so with extra gradient method, so p is equal to 0, because for classical extra gradient method, we assume that Lipschitz continuity of the operator itself, which corresponds to the zero derivative of order 0, and you see that the rate of convergence is proportional to 1 over t, so which means that it is optimal. But for all other p, so if we put here p equal to 1, equal to, and so on, you also see that the rate of convergence increases, and it corresponds to the optimal rate which is possible for this case. This is more or less all what I wanted to show you today. So the conclusion is that indeed the idea of reduced gradient methods so can be extended on high order methods, and moreover, what is important, the explanation and the technique for proving the efficiency of all these high order methods is absolutely the same, starting from the 0 point methods up to order of any degree. So these methods, though, they ensure hot start capabilities, which means that if our starting point is close to the optimum, then the problem becomes simpler. And we see that the high order information increase indeed is useful, and the methods with high order information become fast. Okay, and so I didn't speak about that, but everything is okay with this method. So when we start to work in the neighborhood of non-degenerate solution, where we can have linear and superlinear rate of convergence. Of course, all of that works if we are able to solve auxiliary optimization problems. At this moment, so we can do that for 0 order methods, so where the auxiliary optimization problem usually is just projection, or the first order method, so where the auxiliary minimization problems is just the solution of variation inequalities on a convex set with linear operator, which is also quite simple, but it is important to understand what we can do with the higher order schemes. And here we have a promising example from the third order methods in optimization, where the third order technique, so as we have found recently, so can be implemented using only the second order schemes. So this is all what I wanted to show you today. Thank you.
So if you have a question, comment or remark to this talk, to begin with, maybe I have one. So the variation inequalities, at least an important motivation for them is optimization theory. So some optimization problems for the point of the optimum can be really used in the form of a variation inequality. Now, when you construct this iterational sequence with any method, it turns out that there are hidden optimization problems in the construction of the sequence, like projection to a convex set. This is finding a convex set, finding the closest point to the convex set. That's sort of an optimization problem. So how costful is to handle these little intrinsic optimization problems through the process?
Yes. So this is a good question, just because indeed, so with optimization scheme, we should be careful, because sometimes you can see the papers where with auxiliary problems, methods where auxiliary problems are more difficult than the initial optimization problem. So this, of course, we shouldn't do that. And the main application of the theory are the problems where the computation of the oracle, so in this case, this is the value of this nonlinear operator, is much more difficult than the auxiliary optimization. And this indeed happens in many applications where in order to compute the value of the operator, the derivative of this operator, you need to solve the system of differential equations, or I don't know, do some simulations and something like that. And so this, when the oracle is very difficult, then indeed, so you can forget about the complexity of this simple optimization problem, because indeed in many situations they have very clear structure. We know what is the structure, and we can use this structure of the auxiliary problems in order to have the optimization. Of course, all of that should be taken into account, and so the complete complexity analysis contains all elements. And only after that, so we can say it is reasonable to apply this difficult scheme, so combine it with some projection.
Maybe further corrections.
This example of third order method solving it with the second.
Yes.
Can you just say one or two?
But this is, I would say, mainly the most interesting, let me say, hope which we got recently in optimization, where finally, okay, in optimization theory, we can speak about methods of different order, and as usual, the higher is the order of the scheme, the more powerful it is. The higher is the rate of conversion. But of course, so if you use the high order scheme, so you need to compute high order derivatives and work with the variable tensors where the memory is in cube and things like that. And only recently, so we realized that in optimization, this is not necessary. The third order schemes can be completely replaced by the second order. We can formally apply third order methods with higher rate of conversion, but everything inside will be on the level of the second order. You don't need tensor, you don't need all this strange thing. So all technique is all operations which are inside the scheme, they are typical for the second order schemes. And the reason for that actually is that for convex function, again, so this is a new observation. So third derivative is never big. Third derivative is never big, because third derivative is anti-symmetric, so if you multiply the direction by -1, so it changes the sign. Therefore, if it would be big, it destroys the convexity. Since our function is convex, so the derivative is always small. And it can be approximated somehow using the second order derivatives and the fourth order, or bound for the fourth order. You can remain. And you can have a method so where the rate of convergence is equal to the third order. For example, now there exist second order schemes with the rate of convergence 1 over e to the power 5. And imagine what is it? 5. After 10 iteration, you already have the problem solved. And these are the second orders. This is indeed a very big progress where several years ago people believed that second order schemes cannot converge faster than 1 over e to the power 3. Now we have 5. So this is completely another life. I hope that so the similar things, so we can do the same thing in other fields like variation.
Thank you. Maybe further comments, questions, if any? Maybe to finish, so let me mention that at the Composite University, I believe that the next week, during the next week, there will be a series of lectures delivered by Professor Nesterov. So that our PhD students, I encourage our PhD students to go to Budapest and maybe to attend. How many lectures?
Well, I will have 3 lectures, but it's only 2 days. So,
so 2 days. So it's not going to be, yes. No, 3 lectures in 2 days. That's one can survive. So you need to stay there for 1 night.
Yeah, and maybe I use this opportunity just to have some advertisement. So because we have plans to the series of lectures like that. So this is the first series of 3 lectures. It will be more or less about the complexity theory and the first order schemes. And the next, so we already planned for another 3 lectures that will be all somewhere. It will be about huge scale problem, methods for problems to really exist.
And also let me mention that there are on YouTube you can find some series of lectures related to complex optimization, so you can also watch that. But those PhD students who would like to get the details of this series of lectures at the Composite University, just please send me an email or contact me and I will provide you the details. Okay, so I hope that this was not the end of the story, but just the beginning. I mean, we are not so young to believe in a 60-year continuation of the story, but still maybe it could have some impact on our PhD school and our students if they get this knowledge. So thank you for giving this wonderful lecture, and thank you for attending. Okay. So,